So here we are in chapter 22, alpha carbon chemistry, enols and enolates. So the most important part of this is the alpha carbon, obviously, since we're in alpha carbon chemistry chapter. But when we look at a carbonyl, we look at the first carbon away from the carbonyl is the alpha carbon, and then the second one is the beta, gamma, and delta as you go down the chain. The most important one is the alpha one, because it's the one that, unless we have any other functional groups in the molecule, it's the only one we can do anything with. So we can, with catalytic acid or base, form an enol. En because of the carbon-carbon double bond, the ol because of the alcohol, and the enol can react with an electrophile to add that electrophile on the alpha carbon, or we can add a strong base to the ketone or aldehyde, ester, whatever. The carbonyl alpha carbon can lose a hydrogen off of it to make the enolate 8 because it has the negative charge on the oxygen, and then the enolate can go add to an electrophile to put the electrophile on the alpha carbon. So it's all about what can we add to the alpha carbon in this chapter, and the alpha carbon is the only one that we can do anything to because it's acidic. Because of the resonance structure we can draw for the enolate, putting the negative on the oxygen or on the alpha carbon, of which you should be able to draw the resonance structure going back and forth in that as you're going along. So how can we form the enol or the enolate? Okay, with a catalytic acid or base, with acid we can protonate the carbonyl, then water can come in and remove the extra hydrogen, forming the enol. Or in base we can have the hydroxide grab the hydrogen, form the enolate, and then we can protonate the enolate off of water to make the enol. Okay, both of these have proton transfers in them that are very important as we're going along. The enol is a great nucleophile because of the one resonance structure we have shown at the bottom of the page there, where we can put the negative charge, a negative charge, on the alpha carbon so it can go attack something. If we're in strong base, we would have to remove the alpha hydrogen with our strong base to form the enolate, resonance stabilized anion, and then we'd add acid or water to that to kill it off to make the enol. But the enolate is an ambident nucleophile. It has two sites that it can act as a nucleophile from, either the alpha carbon or the oxygen, and depending on what we add to it, we can add something to either of those sites. But it's just a resonance structure apart, where we can send the electrons up onto the oxygen, or we can send them down from the oxygen to the alpha carbon and go back and forth on that. If the oxygen acts as a nucleophile, attacking an electrophile, we get we still have the carbon-carbon double bond, and we've added something, the electrophile, to the oxygen. If the carbon attacks, we have the carbonyl, and the alpha carbon goes and attacks the electrophile. So it all depends on what we have in the reaction, what we can do with it. Okay, so remember, only the alpha hydrogens are acidic, not any of the other hydrogens. So in this chapter, all we will touch are the alpha hydrogens, alpha, the ones next to the carbonyl. So in this example at the top of the page, we have an aldehyde hydrogen. It is not on the alpha carbon. It is not acidic. We cannot do anything on that with that hydrogen. The only ones that are acidic are the two alpha hydrogens on the carbon adjacent to the carbonyl. So if we look at the bottom of the page, to identify the acidic hydrogens in the following molecule, if we look at this, the first thing we need to do is identify all the alpha positions. These two carbons are alpha to the carbonyl. The carbon on the right, the one with the little red circle, does not have any hydrogens on it, so it has nothing acidic on it. The carbon on the left, with a little red hydrogen drawn in, has a hydrogen on it. It is the only hydrogen that is acidic. It's the only hydrogen we can remove off of that molecule to do anything with it, because it's the only one that has a hydrogen on the alpha carbon. So if we add a base to this, all that's going to happen is the base is going to go grab a hydrogen, and we're going to form the enolate, and our enolate is going to look like that. So we could add something either onto the oxygen or onto the alpha carbon of that, depending on what kind of electrophile we add to it. But that's the only thing we can do to it. So if we have an alpha carbon, we can do two types of bases to it. We can use a really strong base, the LDA, lithium disopropyl amide. It's the anion formed from the disopropyl amine, and the amine has a pK of 36. So it's a very, very strong base. It's very bulky, so it's going to go for the hydrogen on the less substituted side of the carbonyl if there is a difference in them. Okay, so all that's going to happen is it's going to go grab a hydrogen and form the enolate. Form the anion on the alpha carbon, which we can draw resonance structures for, moving it up to the oxygen. And acetaldehyde, all we have is the three equivalent hydrogens on the alpha carbon, so it's just going to take one of them to form the anion. If we look at the dicarbonyl compound shown below, we have two carbonyls and we have two different types of alpha hydrogens. We have the two methyls out on the outside edge of the molecule that are next to one carbonyl, and then we have the two hydrogens in between the two carbonyls. And the two hydrogens in between the two carbonyls are going to be much more acidic, because we can draw a resonance structure, as we'll show down below, where we can send the negative charge out on one oxygen, or we can send it down to the other oxygen. So it gives us a lot more resonance structures that we can draw. So the hydrogens in between the two carbonyls are going to be much more acidic than the hydrogens out on the edge. So we can easily pull those off with a much weaker base than what we'd need to pull off the alpha hydrogens on a plain carbonyl. So we could use ethoxide to pull off the hydrogens in between, because ethanol has a pK of 16. The pK of the diketone is 9, so the equilibrium is far to the right in that we'd have the enolate around, and that enolate we could alkylate with many different alkylating reagents. So depending on what we have around, what kind of base we use, there are different amounts of the enolate that we will have in solution. If we use hydroxide, remember the pK for the first two is going to be in the low 20s. So hydroxide or ethoxide, when it pulls off a hydrogen, it forms water. The pK of water is about 16. The pK of ethanol is about 16. They're all roughly the same. So with hydroxide or ethoxide or any alkoxide, the equilibrium is going to be lying primarily with more ketone involved and a little bit of the enolate, because the equilibrium for the reaction lies strongly towards the left. So we have a little bit of the enolate, not much, but once it forms the enolate, it can go do something else. Sodium hydride or LDA, the conjugate bases are either the amine or hydrogen gas. They both have roughly a pK in the upper 30s. So if the pK for the carbonyl is 21, these are going to be irreversible, because the difference in the pK is so strong, it's going to form the enolate and not be able to go back to the starting ketone based on the difference in pKa's of those reactions. Then if we have the diketone, we can use a weaker base, hydroxide, ethoxide, whatever, and it will nearly completely enolate or form the enolate from this because of the stability of the enolate and how acidic that hydrogen is with its pK somewhere in the around 9 or so. Okay, whereas water has a pK of 16. So it's not going to go back, it's only going to go towards the enolate, and LDA is not necessary in this one because of how acidic that hydrogen is. So here we have one of the first reactions we'll talk about, and it's the alpha halogenation of enols and enolates. And how can we go about doing that? So here in this one, with acidic water and bromine, we can put a bromine on the alpha carbon and do something with it as we're going along. But to draw the mechanism for this, since we're in acid, the first thing we have to do, if we were to show all the arrows for it, is protonate the carbonyl and then draw the resonance structure for that, where we have the positive charge on the carbon, and then we can remove the adjacent hydrogen to form the enol. From the enol, we can have the enol go attack a bromine, kick out a Br, which would give us double bond H with a positive and that alpha bromo, and then water would come in to remove the extra hydrogen off of our carbonyl to get us to the alpha bromo carbonyl. The unsymmetrical ketone shown below, if an unsymmetrical ketone is used, it'll halogenate at the more substituted side. So that's just because of the more stable the alkene is, so we get the bromine added to the more substituted side of the alkene. So what can we do with this once we form the alpha bromo? So in step 1 of this, we're going to turn this into the alpha bromo, and then with pyridine, we can have the pyridine come in and do an elimination to form the alpha beta unsaturated carbonyl. And what I mean by that is alpha and beta. It's between those two carbons, alpha and beta, and it's unsaturated, so you have a carbon-carbon double bond there. We can also do this to carboxylic acids with the Hell-Volhard-Zielinski reaction, bromine PBr3 followed by water. So the sequence of the events is, first we form the acid bromide, then we make the carbon-carbon double bond, removing a hydrogen off of it, protonate the oxygen. Then that can react to add a bromine on the alpha carbon, giving us the bromine on the in place of the OH, and then we can cleave the acid bromide to form the carboxylic acid. Okay, so it's a simple reaction to do in that sense. We have seen under acidic conditions we can do this. We can also do this under basic conditions to alpha halogenate. So with hydroxide, we're going to make the enolate. In this one, since we have the two methyls on the one side, it can only go on one side. And then that enolate can go attack a molecule bromine to add it on. So there's not much to either of the mechanisms of this one. So